Hello, everybody. So for today's video lesson, we're going to be learning about mixed and entire radicals. Okay, so just a refresher from last lesson. So remember, whatever the n is here is going to be the index of our radical. Okay. Whatever is underneath the square root is called the radicand. Okay, so x in this case. And the entire thing here is called the radical. Okay, so first I would like to draw our attention to the multiplication property of radicals. So the product of the radicand is equal to the product of two different factors of that radicand, okay? So the first example we're going to look at, just to kind of give you an example of that, we're going to look at root 12, okay? So root 12 can also be written as root 2 multiplied by root 6. Okay, it can also be written as root 3 times root 4, or it can also be written as root 3 times 2, right? If we simplify that root 4, that will just become 2. Okay, in any case, if we put these into our calculator, we will get 3.46 for all of these values. Okay, so this is just proof of the multiplication property of radicals, that the product of the radicand is equal to the product of two factors of that radicand. Okay, so now we're going to see how many square root expressions we can find for root 60. Okay, so essentially what we're doing here, we're finding the factors of root 60. And then we are just kind of rewriting this, because in some cases it's going to allow us to compare radicals that have different radicands, okay? So root 60 is equivalent to root 60 times root 1, okay? That could be simplified to root 60 times 1, right? Root 1 is equal to 1. We could write root 60 is equal to root 30 times root 2. And we're just going to go along the factor list, okay? So we could do root 15 times root 4, which can be simplified to root 15 times 2. We can do root 10 times root 6. And we could even break up this root 30 into root 10 times root 3 times root 2. Okay, so this is just explaining to you the multiplication property of radicals, that we can break apart a bigger product or a bigger radical into its factor radicals, okay? The big thing there is that the index must be the same for all radicals if we're splitting up that bigger radical. All right. So of all the ways we just wrote the square root expressions, do you think that some are better than others? And why might they be considered better? Okay, so I'd encourage you to pause this video and just consider this question, or go ahead and chat with your peer. Okay, and personally, I think those radicals that have smaller radicands, so like root 4, root 9, those are a little more easier to conceptualize than a root 60, for example. Okay, or if we simplify those into whole numbers, those are a little bit easier for us to kind of deal with if we consider them, okay? So what are going to be considered then others? So those that have smaller radicands or whole numbers, to tie in our lesson from our last lesson. So whole numbers being like 1, 2, 3, 4, the counting numbers. Because we are more familiar with 4 than we are than root 16, for example. Okay, so we have two ways of writing radicals. We have mixed radicals, and this is where we have a number that we have kind of taken out of the radical, okay, once we've simplified it. And then we just have entire radicals where it's just going to be the radical, okay? So when we have a mixed radical like up here, that's going to be considered the simplest form. And maybe an analogy for mixed radicals and entire radicals. Think of entire radicals as an unsimplified fraction. And then a mixed radical is like a fully reduced fraction, okay? So an example of a mixed radical might be 2 root 3. Okay, and then an entire radical might just be like root 12. All right, and we will get into simplifying these radicals in the next couple of slides here. So there are a couple ways that we can convert between the two. We have looked at prime factorization in depth throughout the last unit and a half. And another strategy is using perfect roots, okay? So prime factorization. This is where we're using factor trees to determine the prime numbers that multiply to form a product that we are trying to simplify. Okay, so let's do an example here. So for example, let's do root 16. Okay, so the factor tree of 16 would be 2 and 8, 2 and 4, and 2 and 2. So we can rewrite root 16 as 2 times 2 times 2 times 2. Remember, we are using, or when we're doing square roots, we're looking for pairs. Okay, so note that we have 2 pairs here. So once we have a pair, we can take it outside. So I'm going to simplify this in 2 steps. So this is, so once you have a pair, so it's 2 times 2 is equal to 4. And then if we take the square root of 4, it equals 2, right? And then we're still going to have those 2 2's still left inside because we haven't taken them out yet, right? Now we have another pair of 2's. So 2 times 2 is 4. Root 4 is 2, okay? And then if you're taking out another pair, you have to multiply it by what you've already taken out. So that equals 4, right? The square root of 16 is equal to 4. Okay, so that's prime factorization. We're going to talk about perfect roots next. So this uses perfect square factors to quickly simplify a radical expression. Okay, so this takes kind of a little bit of remembering or a little bit of knowledge of what our perfect squares and our perfect cubes are. Okay, so remember our perfect squares are 1 times 1 is 1, 2 times 2 is 4, 3 times 3 is 9, 4 times 4 is 16, 25, etc. And then we have our perfect cubes as well. One times one times one is 1, 2 times 2 times 2 is 8, 3 times 3 times 3 is 27, etc. Okay, so whatever method you prefer is totally up to you. My only ask is that you show all of your work when you're going through these, okay? So I'm gonna go and show you both strategies. It would be nice if you were to try a couple of these strategies, or like use perfect squares and prime factorization strategies for each. And then if you're like, oh, I like perfect squares, or you're familiar with prime factorization, that's all good. There might be cases where one strategy is more efficient than the other, okay? But whatever strategy you decide to use is totally up to you. Okay, so perfect squares. So we're starting with 75, and now we're going to try to factor 75 into our perfect squares. Okay, so remember perfect squares 1, 4, 9, 16, 25, 36. And I do now realize that 75 is a factor of 25 and 3. Okay. So now we can rewrite this. So root 75 can be rewritten as root 25 times root 3. That equals root 75. Okay, and if we take the square root of 25, that is just 5. Okay, so we'll take that outside. And because 3 is not a perfect square, we're just going to go ahead and leave that inside the root, okay? So that is going to simplify to 5 root 3. Okay, again, that 5 comes from the square root of 25, and there is the root 3 is not a perfect square, so we just have to leave that alone. Okay, prime factorization. So we're just going to break 75 down into our factor trees. Okay, so 75, this one's going to look very similar. So 5 is a factor of 75, so 5 and 15, 5 and 3. Okay, so we can rewrite root 75 as 5 times 5 times 3. We are taking the square root here, so we're looking for pairs. Once you found a pair, you take that outside of the bracket, and that becomes 5 root 3 as well. Okay, so a little bit different strategies, but we still arrive at the same answer. So again, whatever strategy you like more, feel free to roll with that. But I would encourage you to continue to try both. Okay, so let's start with prime factorization this time. So 18 breaks down in its factor tree to 2 and 9, and 9 is 3 and 3. Okay, so root 18 is equal to root 2 times 3 times 3. We are looking for pairs because it's square root. We have 2 3s right there. So we'll take that 3 outside. So that is going to simplify to 3 root 2. Again, 2 is a prime number. So we're going to leave that alone. Okay, so 18, how can we break 18 down into a prime number? I know it is 9 and 2. So root 18 is equal to root 9 times 2. There we have a root 9, which we can bring outside because it's a perfect square. So that is going to equal 3 root 2. Okay, so the perfect square method does kind of use a little bit more mental math and a little bit more knowledge of those perfect squares. Prime factorization, it ties into what we've been doing for the last few weeks. So again, do whatever strategy works for you. Okay, so big thing here, watch out if we're looking for perfect squares or perfect cubes, okay? Because if we're doing perfect cubes, we're going to be looking for triplets, okay? Now for perfect cubes, a little bit more unfamiliar with them. So let's just go ahead and write these down. So 1 times 1 times 1 is 1. 2 times 2 times 2 is 8. 3 times 3 times 3 is 27. 64 is 4. And why I'm doing this, so remember our multiplication radical rule from a few slides back? Multiplication property of radicals. As long as our roots are okay, the product, we're just looking for 2 factors. So I'm trying to look for a perfect cube factor of 144, okay? And factors of 144, if you're not sure, you can do a factor tree. So 1 and 144, 2 and 72, 4 and 36, then for 5, 8 and 18. And that's awesome there because that is a perfect cube there. Okay, so we can write 144 as a factor of 8 and 18. So the cube root of 144 is equal to the cube root of 8 times 18. 8 times 18. Okay, and because the cube root of 8 is 2, I'm going to pull that 8 outside of the radical. And because 18 is not a perfect cube, I'm just going to leave that inside. Okay, so that can simplify to 2 cube root 18. Okay, so again, that one takes a little bit more work, just because I'm not as familiar with the perfect cubes as I am with the perfect squares. Let's check our answer with prime factorization. Okay, so 144 is 2 and 77. Uh, 72, excuse me. I know that didn't sound right. And then 2 and 36. 2 and 18. 2 and 9. 3 and 3. All right. And so let's go ahead and rewrite this. And remember, we're looking for groups of 3 here. So the cube root of 144 is equal to the cube root of 2 times 2 times 2 times 2 times 3 times 3. I see 3 2's sitting right there. All right. So let's go ahead and take those outside. Okay. And now whatever's left inside the radical. Okay, so we have 2, 3, and 3 left in there. Okay, because I don't have any groups of 3, we're just going to go ahead and multiply those together. So 3 times 3 is 9, times 2 is 18. And voila, we get the same answer, which is great. Okay, so this one we're doing perfect fourths. So again, I'm not very familiar with my perfect fourths, so let's just go ahead and write them down. So 1 times 1 times 1 times 1 is 1. 2 times 2 is 4, times 2 is 8, times 2 is 16. 3 times 3 is 9, times 3 is 27, times 3 is 81. Okay, so we've gone past 32, but I recognize that 32 as a product has 16 and 2 as its factors. So the 4th root of 32 is equal to the 4th root of 16 times the 4th root of 2. The 4th root of 16 is equal to 2 times the 4th root of 2. Okay, prime factorization using our factor trees. So 32 breaks down to 2 and 16, 2 and 8, 2 and 4, and 2 and 2. Okay, so 4th root of 32 is equal to the 4th root of 2 times 2 times 2 times 2 times 2. Take out a group of 4 because we're doing perfect fourths. And that equals 2 4th roots of whatever's left behind and just 1, 2. Okay. So now that we've done a couple, you can try this one on your own. Feel free to pause the video. Using perfect squares. So what are the factors of 30? So we have 1 and 30, 2 and 15, 3 and 10. No numbers there are perfect squares. Okay, so let's jump over to prime factorization to see if we can simplify this 30. Okay, so 30 is 2 and 15, and 3 and 5. There are no pairs there. Cannot simplify. Okay, sorry if you took a couple minutes and you're banging your head against the table because you couldn't find any factors there. But good job if you noticed that. Okay, so now we're going the other way. So we have a mixed radical and we want to put it into an entire radical. So remember when we were taking this number out, it was because we had a pair of them. So going the other way, if we have a number out front, that means we've taken out 2 of them from the radicand. Okay, so this is just going to equal the 5 that's already in there multiplied by the 2 3s that have already been taken out. Okay, so 3 times 3 is 9. 9 times 5 is 45. So this can simplify or unsimplify to root 45 as an entire radical. Okay, so try these other 2 on your own. Feel free to pause the video. So we've taken out a pair of 4s. So let's put those 4s back in. 3 times 4 times 4. Okay, 4 times 4 is 16. 16 times 3 is 32. Or excuse me, 40. 16 times 2 is 32. Times 1 more is 48. So that is going to equal 48. Okay, so we've taken out a pair of 5s. That 10 was already in there. So 5 times 5 is 25. 25 times 10 is 250. Okay, not too bad, hopefully. Okay, so again, if we do not see a number right there, the index, it is assumed that we're taking the square root. Okay, so when we're taking square roots, we're taking out pairs. If we're simplifying radicals, or if we're unsimplifying them, if we're turning them to entire radicals, we were looking for pairs, or we're going to put 2 back in. Now we are taking the cube root. So now all we're going to do is put back in 3 of whatever number has been taken out. Okay, and don't forget that cube root up there. So 6 times 2 times 2 times 2. So 2 times 2 is 4, times 2 is 8. And then 8 times 6 is 48. So that would equal the cube root of 48. Okay, again, I would encourage you to try these last ones on your own. That equals the 4th root of the 7 that was in there before, times 4, times 4, times 4, times 4. Okay, I'm not going to do this one in my head, a little too big. But that is going to equal the 4th root of 1,792. Okay, last one here, it's the 5th root. So we've taken out 5 2's. So we're going to put 5 2's back in. And there was 1 there to begin with. Okay, so 2 to the 6, essentially. So 2, 4, 8, 16, 32, 64. So that is equal to the 5th root of 64. All right. Okay, so that is mixed and entire radicals. So converting between the two, doing what we just did here, and also simplifying them. I'm not going to make you do perfect square simplification if you prefer prime factorization. Okay, I'm not too bothered on which strategy you use, as long as, of course, you are showing your work. Okay, but you will need to be able to convert from a mixed radical into an entire radical, or from an entire radical into a mixed radical. Okay. If you have any questions, please feel free to send me an email. Other than that, thanks for your attention. Have a great day.